NASA didn't announce it with a giant headline, "No, aliens confirmed" banner. Instead, it showed up in cautious words, in a few images, in a handful of chemical clues that, when you stack them together, feel like a door cracking open. Because on Mars, NASA has found something that doesn't just suggest the planet used to be wet. It suggests Mars may have been habitable longer, in more places, and in more complicated ways than we thought. And that changes what we do next. For decades, Mars has been two planets in one. From orbit, it looks dead, a cold desert with a thin atmosphere and dust storms that can swallow continents. But on the ground, it keeps revealing a second identity, an ancient world shaped by rivers, lakes, and chemistry that looks uncomfortably familiar. NASA's rovers have spent years chasing one question: did Mars ever have the ingredients and conditions for life? Not did life happen, but could it have? And that sounds like a small difference until you realize how high the stakes are. If habitable environments were rare and brief, then even microbial life would be a long shot. But if habitable environments were widespread and persisted, then Mars stops being a dead rock and becomes a world that may have hosted biology and might still preserve its fingerprints. The something NASA found isn't one object. It's a pattern built from rock layers, minerals, and organic chemistry, pointing to a Mars that stayed livable longer than expected. Start at Jezero Crater, where the Perseverance rover landed. Jezero isn't random. It's a fossil lake basin, complete with a river delta frozen in stone. Deltas are special because they're nature's filing cabinets. Flowing water drops sediments in layers, trapping whatever chemistry, and potentially biology, was present at the time. Perseverance rolled up to those delta deposits expecting a clear story. River brings sediment, lake collects it, time passes, end of chapter. But the rocks didn't cooperate. The rover found evidence of changing water levels, different flow energies, and multiple episodes of deposition. That matters because it hints Jezero wasn't a single short-lived pond. It behaved more like a system, one that evolved, returned, and reworked itself. Then the mineral story got more interesting. In several places, Perseverance identified clays and carbonates, minerals that typically form in water and can lock away chemical information for billions of years. Clays can preserve organics by shielding them from radiation. Carbonates can act like a snapshot of ancient water chemistry, including pH and dissolved CO2. If Mars was only briefly wet, you expect simple layers, one wet phase, then dryness. Jezero's rocks look more like a book with missing pages and multiple editions. Here's where headlines get reckless. NASA has detected organic molecules on Mars, more than once, with multiple missions. Curiosity found organics in Jezero Crater, including complex carbon-containing compounds in ancient mudstones. Perseverance has also reported organics in Jezero materials. But organic does not mean alive. Organic chemistry is the chemistry of carbon-based molecules, and it can come from non-biological sources, meteorites, geology, or chemical reactions powered by heat and water. So why is this still a big deal? Because context matters. Organics on their own are like a single letter torn out of a book. But organics found in ancient lakebed sediments, alongside minerals that preserve chemistry, inside rocks that formed in watery environments? That's more like finding a letter still inside the envelope, with the date, location, and fingerprints intact. Even more intriguing, some organics appear associated with sulfate-rich rocks and altered minerals. On Earth, environments with shifting water chemistry, wet-dry cycles, changing salinity, can concentrate organics and create micro-niches where microbes thrive. The real discovery isn't NASA found organics, it's NASA found organics in places where Mars was doing the kinds of chemistry that, on Earth, makes life's building blocks easier to preserve. One of the biggest changes in how we see Mars is this: the planet wasn't simply wet, then dead. The evidence increasingly points to a messy timeline, periods of stable water, then drying, then water returning in different forms. Curiosity's climb up Mount Sharp and Jezero Crater revealed shifting environments across layers, from lakebed mudstones to more arid, wind-shaped deposits, to sulfate-bearing layers that suggest changing water chemistry and potentially more acidic conditions. That tells us Mars didn't just lose water, it transformed the way water interacted with rock. Perseverance, meanwhile, has been exploring crater floor materials that may include igneous rocks altered by water, meaning water didn't only pool on the surface, it may have circulated through the crust. And when water moves through rock, it can create energy gradients, chemical batteries, especially where different minerals meet. This is where the something NASA found starts to feel like a turning point. The accumulating evidence suggests multiple habitable settings, not just one. Lakes, deltas, groundwater-altered rocks, possibly hydrothermal or water-rock reactions that could feed microbial ecosystems. Mars begins to look less like a planet that missed its chance and more like a planet that had several chances over long stretches of time. If Mars ever hosted life, it probably wasn't dinosaurs. It would have been microbes, tiny, stubborn, chemical opportunists. And microbes don't leave skeletons. They leave subtle traces, textures in rock, unusual concentrations of elements, or chemical preferences that biology tends to produce. That's why NASA's strategy has shifted from drive and analyze to something bigger: sample return. Perseverance isn't just studying rocks, it's selecting, drilling, sealing, and caching samples that represent different environments: lake sediments, altered rocks, mineral-rich layers that might preserve biosignatures. Because rover instruments are amazing, but they're still field kits, the real lab is on Earth, with techniques that can separate and measure isotopes, detect ultra-trace organics, and test multiple hypotheses against the same sample. And this is crucial. The something NASA found includes rocks that are good at preserving evidence: fine-grained sediments, clay-rich layers, carbonates, materials that on Earth can preserve microfossils and organics for unimaginable spans of time. Mars isn't just giving us clues, it's offering us physical evidence we can put under the most powerful microscopes humans have ever built. So what's the something that changes everything? It's the realization that Mars wasn't merely wet, it was persistently and repeatedly habitable in different ways, and it preserved the record well enough that we have a real shot at testing the life question properly. For years, skeptics could argue, sure, Mars had water, but maybe it was brief, harsh, and sterilizing. Now the rover evidence increasingly supports a Mars with long-lived lakes, evolving chemistry, groundwater interactions, and minerals that protect organics. That doesn't prove life existed, but it dramatically upgrades the odds that if life ever started, or ever arrived, it had time and places to persist. And it reframes the mission. We're no longer just exploring a dead planet for interesting geology. We're doing something closer to planetary archaeology, collecting a curated set of samples from environments that could have supported life and could have preserved its traces. The twist is simple. The biggest discovery isn't a fossil. It's a map of where to look, what to bring back, and how close we might be to an answer that would rewrite biology. NASA didn't find a smoking gun on Mars. It found something more powerful, a growing, consistent story told by rocks, minerals, and organics, pointing to a planet that stayed habitable longer than we once believed. And if Perseverance's samples make it back to Earth, the next something NASA finds might not be a clue. It might be a conclusion.